Hi, my name is Changlong Wu from University of Hawaii at Manoa. So in this talk, I'm going to present the paper Non-Uniform Consistency of Online Learning with Random Sampling. And this is a joint work with my advisor, Narayana Santhanam. Okay, the problem we'll consider in this paper is as follows. So we have the instance space X, and which is also a measure space. And we also have a probability measure mu over X. And we consider a class H, which is a class of measurable functions from the instance X to the 0 and 1. And we consider a randomized online learning scenario. So there are two parties in this scenario, the nature and the learner. At the beginning, the nature will choose some function h from the class, and at each time step n, the nature will sample a value xn from the probability measure mu independently. And the learner will then provide a prediction of the label of xn given by h, potentially use the history observed thus far. And also, the nature will reveal the true label after the prediction has been made. And we're interested in the following problem. So we're interested in under what conditions on the class H, the probability measure mu, and also the instance space X, the learner could only make finite many errors, or most surely in the infinite horizon, no matter what the H is chosen by the nature at the beginning. Okay, to put it more formally, we'll consider the following definition. So we say a class H together with the distribution mu to be eventually or most surely or EAS online learnable if there exists a prediction rule of phi, where phi possibly depends on the distribution mu, such that for all h chosen by the nature, we have the probability of the cumulative sum of the errors is finite, is 1, where the probability depends on all the randomness that is involved in the process, including the randomness comes from the independent sample and also the internal randomness that is used by phi. So we need to emphasize that the EES online learnability is a distribution-dependent setting. And we use a different notion, the strongly EES learnability to denote the distribution independent setting. We say a class H to be strongly EES learnable if there exists a universal prediction rule of phi that works for all distribution. Okay, before we go to our main result, we first review some related work. So the randomized online learning scenario was first considered by Hosner et al., where they show that if a class has finite basic dimension, then we can achieve an expected error at step n to be upper bounded by 1 over n. And they also show that for finite basic dimension classes, if the class is non-trivial, then you cannot improve the 1 over n bound. However, the normal bound is distribution independent. Sherman later showed a non-uniform expected lower bound of 1 over n for the linear spatial function and for the uniform distribution over the interval from 0 to the 1. So here, the Sherman's bound is actually non-uniform, meaning that the constant hidden by the omega can be dependent on the distribution. Actually, here it is dependent on the uniform distribution and can be dependent also on the individual hypothesis. And Busquet et al. Recently provided a complete characterization for the non-uniform expected rate in a weak realizable setting. By weak here, we mean that the functions that are chosen by the nature may not necessarily come from the class H. The only requirement is that any finite length of the sample must be consistent with some function in the class. So it is possible that for different lengths of the sample, the function that is consistent with it is different. So there may not exist a unique function in the class that is consistent with all the samples, with all the infinite samples. And we will discuss this later. And all these results are considering the guarantee for the expected error rate. However, the expected error rate cannot be translated into a guarantee for the errors that holds also almost surely, because the predictions at each time step are dependent, because the prediction at some time step depends on its previous observations. So this makes it hard to apply the standard concentration inequality, especially to establish the lower bound. Okay, so when I'm ready to state our main result is that assuming the sigma algebra over X is countably generated, then a class H together with the distribution mu is EAS online learnable if and only if H is effectively countable. Here, by effectively countable, we mean that there exists a countable class H prime such that for any function in H, there exists another function in the H prime. We have the measure of the difference setup between these two functions is 0. Okay, so in our theorem, we have an assumption on the sigma algebra of X, but this assumption is very weak because most of the natural sigma algebras are indeed countably generated. For example, the Fourier sigma algebra over the R to the D. Okay, we give some corollary of our main result. The first corollary is that the class of all linear threshold functions with uniform distribution over 0 to the 1 is not ES unlearnable because the class of all linear threshold functions is uncountable. And this actually gives us a lower bound of 1 over n log to the 1 plus epsilon n for the expected error. And this lower bound actually differs only a polynomial term compared to the lower bound of Schurman's. And this follows directly from the Fourier-Cartesian lemma. And we also have the following characterization for the finite little stone dimensional classes. So we show that for any class of measurable functions, if the class has finite little stone dimension, then the restriction of the function on any countable subset of the domain must be countable. Okay. So we now show some key ingredient that is necessary to establish our main result. We first need the following lemma. The lemma basically says that suppose we have countable classes, and each of the classes is ES non-learnable with respect to the same distribution mu, then the union of all these classes will also be ES non-learnable with respect to the mu. And the proof is as follows. And because each of the classes HK is ES predictable, ES non-learnable, then we have a prediction rule of phi k that makes only finitely many errors with probability 1, no matter what the function is chosen from HK. And we will denote EKN to be the number of errors that phi k would have made on current samples up to step n, where EKN is basically the empirical error that phi k would have made on current samples. And at time step n plus 1, we will use phi in to make the prediction, where in is given by the eigenminimum of the index plus the EKN, the empirical error. And this is basically a structural risk minimization. And we can show that this rule will indeed make only finitely many errors with probability 1, no matter what function is chosen from H. Clearly, the sufficiency follows immediately from the lemma. However, the proof necessary condition is more involved, and we split the proof into several steps. So in step 1, we show that if a class is ES non-learnable, then it can be decomposed into a countable union of subclasses, where each subclass Hn admits a predictor that makes no errors of step n with probability at least 3 or 4. And then we claim that for all n, the infaming of the distance between any two functions h1 and h2 in the subclass Hn, where the h1 and h2 differs a positive measure, then the infaming of the distance among all these h1 and h2s will be strictly positive. And we define such an infaming to be the epsilon n. Basically, what we're doing is we will show that the epsilon n will be strictly positive for all n. And to say this, to say why the epsilon n is strictly positive, we are assuming that for some n, the epsilon n equals to 0. Then we can find two functions h1 and h2 belong to the class Hn, so that the distance between the h1 and h2 is small enough and yet greater than 0. Because it is small, because the distance is small enough, then with high probability we cannot distinguish them with only n steps. However, because they also differ a positive measures set, with probability 1, the samples that come from the h1 and h2 will differ at some final point, and this point will larger than n. So at this point, any predictor must make an error for either h1 or h2, because before that the samples are the same, but it differs at this point. And using a probabilistic argument, we can show that any predictor must make an error for either h1 or h2 with probability at least 1 over 4. And this will warrant the property that there exists a predictor for Hn so that it makes no errors of a step with probability at least 3 over 4. Okay, so now we have shown that the epsilon n will greater than 0 for all n, and this will imply that the Hn will be effectively countable. This is because the sigma algebra of the X is countably generated. And because countable generated will imply there is a dense countable, or the countable dense subset of the measurable functions. Okay, as we discussed before, Busquet et al. Recently showed that, among other things, a class H can be learned with finitely many errors in the online fashion and in the weak realizable setting if and only if the function has no infinite disjoint tree. However, this does not hold in the strong realizable case that we consider in this talk, where strong realizable means that the function that is chosen by the nature must come from the class. Recall that the weak realizable only requires the finite length of the sample will be consistent with some function in the class. It does not require the function chosen by nature comes from the class H. And this follows actually very easily because we can consider the class of linear functions with rational parameters. And this class has infinitely discriminatory, but it also can be strongly ES non-learnable because it is countable. The initial question is that can all the strongly ES non-learnable class can be decomposed as a countable unit of classes with no infinitely discriminatory? Okay, and we can show that this is actually not true. And we have the following counterexample, and this counterexample was inspired actually by example of Bosco et al. And the construction goes as follows. And we can show that there actually exists a prediction rule that makes only finitely errors, no matter what function is chosen from the H. And the prediction rule goes as follows. And another nice property is that the H cannot be decomposed into countable classes such that all the subclasses has no infinite discriminatory, because any countable decomposition must have an infinite component, and such a component must have an infinite discriminatory. Okay, so from our characterization for the EES non-learnability, our main result, which shows that if a class is strongly EES non-learnable, then the restriction of the class on any countable subset of the domain is countable. And we're interested in whether the converse is true or not. And we have the following open problem. The open problem basically asks that if the restriction of the class on any countable subset of the domain is countable, does it mean that the class is strongly EES non-learnable? Okay, we have some general results which consider the general prediction problems and non-i.i.d settings, and which is available from arXiv. And the conference origin to appear in the AS days. Okay, thank you.